Now, finding the domain of the quotient of functions is very similar to finding the domain of the sum, difference, and product of two functions. So these are the 8 examples that we are going to be going over in this case. So in example 1, we have f of x equal x minus 3 and g of x equal to square root of x plus 5. In the function f, we know right away that since we don't have any denominator, the domain is going to be all real numbers from negative infinity to positive infinity. In the function g, since we have square root of x, we want to take the inside of the radical and we want to set it greater than or equal to 0 and solve for x. But the inside of this radical, we just want to be the x variable. So setting it greater than or equal to 0, we already solved for x, which is x has to be greater than or equal to 0. And the interval notation for this is going to be half closed, half open, closed at 0, which is a bracket, and open at infinity as always. Now, if we take f of x and divide it by g of x, we are going to have x minus 3 over square root of x plus 5. Every time we see a rational equation like this and we want to find the domains, well, the first thing we always tend to do is that we take the denominator, set it not equal to 0, set it not equal to 0, my bad, and we solve for x by subtracting 5 to both sides. We're left with just square root of x, which cannot be equal to negative 5. Solving for x by getting rid of the square root, by taking the exponential power of 2 to both sides, we have x cannot be equal to 25. But that's going to be a little odd because assuming that x is 25, we plug it into this denominator, we got square root of 25, which is just 5, and then we got 5 plus 5, which is 10. And with the denominator being 10, it's going to give us like a valid fraction. So really, in this particular example, the way we find the domain of this quotient is that instead of taking the whole denominator and set it not equal to 0, we just take the inside of this radical and we set it greater than or equal to 0. But the inside of this radical is, again, just as in the function g, it's just the x. So really, we just, well, let's cross this out. We just have x right here, greater than or equal to 0. And what about g over f? Well, g of x divided by f of x is going to be equal to square root of x plus 5 over x minus 3. Again, we have a rational expression, so take the denominator and set it not equal to 0 to solve for x in order to find the domain. By adding 3 to both sides, x cannot be equal to positive 3. Okay, so let's see. Interval notation for this is going to be from 0 all the way to infinity, half closed, half open, just like in the function g. For this one, it's going to be from negative infinity all the way to 3, union from 3 all the way to infinity. Okay, now this is just the interval notation for what I got here. We actually have to do it this way. So if you guys do something like this, I recommend not to, because we're actually missing one more step in this case, which is this one right here. Because again, we have to note that every time we have a square root, or when we have any even root, I should say, your x values has to be at least 0 or above, just like up here. So really, we have another restriction of x has to be greater than or equal to 0. Not just x cannot be equal to 3. Because 1, if x equals to 3, then we would have the denominator of 0, which would make this whole fraction undefined. If x is anything less than 0, then this whole fraction will be undefined as well. Because, again, every time we have even roots, x has to be at least 0 or above. So we actually have 2 restrictions in this case. Now, how do we graph it out on a number line? So let me cross this out because I purposely do this for you guys to see. Because I'm pretty sure a lot of you guys tend to jump straight into what I'm crossing out here. But anyway, on a number line, for f over g of x. Let's say we got this right here. We get 0, and now I'm just gonna put 0 like that. Right there. Let's see. On the number line for the function f, the domain is all real numbers, so we're going from negative infinity all the way to positive infinity, like that. For the function g, the domain has to be that x has to be at least 0 or above. So it looks something like that. And of course, it is going to be a closed dot because we have the inequality of greater than or equal. If we only have greater than, which is strictly greater than in another word, or strictly less than, it's going to be open circle. So this is the graph of domain of function f, function g, and x doesn't have any restriction. G has a restriction of x being at least 0 or above, and the whole process of simplification here only consists of this steps where the restriction is also that x has to be at least 0 or above. So really, the domain of f over g, if we want to graph it on this number line, has to be all of the x values in common of both domain of f and g. And the way we can do that is by taking the shorter domain, which is the one of the g, trace it all the way back to the number line, and we can tell right away that all of the x values they have in common are just all of the x values from here. So the domain of f over g graphically is going to be from 0 all the way to infinity. So the interval notation is that. Now what about g over f? We'll sketch a number line again. And I'll make it a little longer in this case. And the same thing. Just go ahead and graph the domain of the function f, function g on this number line. So this is the function, domain of function f. And the one in red is the domain of function g. And of course, again, because the domain of the function g has the inequality side of greater than or equal, so that's a closed dot. But at the same time, we have the restriction that 1, x cannot be equal to 3. So let's have an open circle right here. And 2, x has to be at least 0 or above. So be right there. So I'm gonna name this I'm gonna name this lowercase a, and this restriction lowercase b. So this is lowercase a and this is lowercase b. With the domain of the function f and the domain of the function g and both of the restrictions, the domain of g over f has to include all of the x values in common of both domains of f and g, and all of the restrictions from the function f, which we don't have any, from the function g, which is x being at least 0 or above, and all of the restrictions in this entire process of simplification, which is just these two. And putting everything together, and well, let's trace it up here first. We can tell that all the x values in common of both f and g is going to be at least 0 all the way to infinity. And putting together all of the restriction as well, which is these two, we have domain of g over f. And the interval notation is going to be going from here to here. Is going to be half closed, half open interval. Oops, this is 3, my bad, not infinity. So from here to here is a half closed, half open interval from 0 to 3, including 0 but excluding 3. And then jumping to the next part, which is the union side, from excluding 3 all the way to infinity. And it's an open interval. And this is how we find the domain of these two quotients of these two functions.